We're picking up where we left off with number 7. This is the second half of our Unit 2 practice test. Here we go. What are the zeros and vertical asymptotes of this fraction? So there are two parts to this question. The first part we're going to answer is, what are the zeros? To find the zeros, you need to set the numerator equal to 0 and solve for x. But do you know why? Well, because any fraction, doesn't matter what's in the numerator, it doesn't matter what's in the denominator. If the numerator is 0, it's equal to 0. So that is how we find our zeros. So we take the numerator, set it equal to 0, and hopefully you notice that you have x's in all three terms. So we want to factor that out. Because remember, to find zeros, we need to fully factor this, okay? And then set each factor equal to 0 and solve for x. Now, we have factored out x already. So that is a factor, and when we set that equal to 0, there's no more work that needs to be done. So we've actually already found one of the three. Make sure you don't forget it. It's a good idea to write that answer wherever you're going to put the rest of your answers so you make sure to not leave it out. But what about this inside parentheses? Is this fully factored? Clearly, it's not. We have a quadratic with a leading coefficient of 2. So you could use factor by grouping if you choose to do that. If not, you can use the quadratic formula, which is what I'm going to do right now. Okay, so the main priority is factor this quadratic, all of this in the parentheses. So we use our quadratic formula. What's most important is to correctly first identify A, coefficient of x squared, B, coefficient of x, and C, the constant. And now we substitute all of these values into our quadratic formula, and that's what you see here. Now you need to be very careful that you put all the values in the right places and complete all the operations carefully, because there is a lot of room for mistakes. Here we can quickly do -1 times 1 gives us -1, 2 times 2, 4. Those are pretty simple. But what about the radicand here? There's a lot going on. Follow the rules of PEMDAS. 1 squared is 1. And then there's multiplication. If you multiply that out, you get -8 times -3 to give you +24. Luckily, we get a perfect square when you add those together. So the square root of 25 is 5. But what does it mean if you have a plus and a minus sign? You should remember that means you have two different zeros that are going to come out of it, which is perfect because in this numerator, the highest power of 3 tells us how many zeros we're going to get. So we already have the 1 from earlier, and now it's time to get the two others. So we have the positive case and the negative case. So here we add and divide to get 1. Here we subtract and divide to get -3/2. So we found the zeros. Great, but now we need to find the vertical asymptotes. So let's talk about vertical asymptotes for a moment. On a graph, you know they look like this. It's a boundary line where your graph line will never touch or cross. This cannot happen, right? It will get close, but it's never going to touch. So your graph line might look, I don't know, let's say something like that. I'm not saying this is accurate to what we are working with here, just the general idea of vertical asymptotes, okay? But what's the equation of a vertical asymptote look like? It's always x equals some number, right? Well, didn't we just find that if we factor and use the zero product property, we find out what x equals? We did. But now we want to know specifically what's going to make the denominator equal to zero because we're looking for a vertical asymptote. That is a place our line cannot touch. And think about any fraction with a denominator of zero. What does that equal? Undefined, which totally makes sense. If we find the values that make the denominator equal to zero, we're going to find out where those vertical asymptotes are. In other words, where this quadratic is undefined. So take a look at what we have. We're going to take it out of the denominator and set it equal to zero. And now we're really going to focus here. What do we have? Well, we have a quadratic with a leading coefficient of 1. Hopefully you know by now that means you can use the x method and that's all you need to do. So we don't need the quadratic formula here because of that leading coefficient. What a guy. All right, so we take a times c on top, b on bottom. 3 and 2 multiply to 6 and add to 5, so we know we have the right values. Remember, this is how you set up your factors, where this value goes here and this one goes there. Most of the work is done. We just take each of these factors, set them equal to 0, and solve for x. So we actually have two vertical asymptotes. We're not asked to graph, so we're not going to graph, but reminder there of what it looks like if you did. Number 8, please do not just draw a graph. If you just decide to go, okay, I'm going to draw a y-axis and then an x-axis and just graph my line, is that going to help you when you look at it? Probably not, right? You need to know, how did I get that line? And that's really what this is all about. So here are some brief explanations. This is your parent function with all possible transformations, okay? And here's the function we have. It's a square root function or a radical function. And what's the deal? Well, we have 2 out front. Well, that's going to be a. That's athletic A, so vertical stretch by a factor of 2. Let's look at the parent function, which is this blue line, for a second to really understand what's happening here. These are the 3 key points I asked you to really make sure you are aware of, because when transformations happen, those will guide us, okay? So a vertical stretch, what value is getting changed? The y values, right? Because y represents vertical movement, okay? And by what? By a factor of 2. What does a factor mean? Well, that means you're multiplying by 2. So we're going to take every y value and multiply by 2 to find the new points of our stretched line. Well, 0 times 2, that's just 0, so that point stays right where it's at. Here you get 1 comma 2, because we're multiplying again, that 1 times 2, so we'll have a point there. And then 2 times 2, so we're going to have the point 4. I know that's hard to see. Let's make it a little easier to see. We're going to have a point right around here that's going to be 4, 4. And if I draw that line connecting those dots, does it look similar to the red line? Very much so, right? So that's how we stretch it. And then h, take a look at our function again. H is here. Dishonest h is the opposite sign, so 2. So we're moving horizontally right 2 units. Take a look. Every point moved right 2 units. Every single point. So to recap, the blue line is our parent function, and the red line is our transformed function on a graph. Number 9, what effect does replacing x with x plus 2 have on the graph of this function? So ultimately they're saying, hey, what happens if you take that x and instead you put x plus 2 there? So we start off, we substitute, we replace just like they asked us to, and we need to work out what's going on between these absolute value lines. So we have this, and we're following the rules of PEMDAS. Can we do anything inside the parentheses? No, not like terms. Are there exponents? Yes, technically everything here is to the power of 1, but that doesn't really help us much, so no, nothing really to do there. Is there multiplication? Well, this is minus 4. If that was out front, that would be multiplication, but that's not the case. So since there's no multiplication happening, and parentheses mean multiply, we don't need them anymore, do we? So only one thing left to do, combine like terms, x minus 2, which we see right there. So back to the question at hand, what effect did it have? Well, let's take a look. In our original function, h was 4. Now, h is 2. So if h was, we're just going to use the x-axis. We don't care about the y, right? We're just talking about the horizontal movement. If we went from 4 to 2, that means there was a horizontal shift 2 units to the left. Okay. Number 10. We did this before. Hopefully this jogs your memory. There's some visuals here, but this work really is in Desmos graphing calculator. We're asked which quadratic function best fits this data. You have data in the table. So we're going to take that data and put it into a table in Desmos by going to this website, click the plus, and then table. From there, you're just looking at your table with your values and putting them in, all your x's and your y's. Then you want to click in box 2, just below box 1 where you made your table, and type this in, okay? If you need help typing this in, these are the exact keys you need to type. And something really amazing is going to happen when you do that. You're going to get all of this great information. Here you see that that you typed in from there. There it is. And here, just below, you see A equals this, and then B and C. Those are your values in your equation. See, A, B, and C. There is a little rounding going on. If you're asked to round, make sure you do that. And we have Y with the little up arrow above it. Just quick reminder, this symbol and this symbol both mean approximately equal. So the Desmos graphing calculator will give you everything you need, other than you typing it in, of course. Number 11. A number of birds were released into a forest preserve with a carrying capacity of 500 birds. That carrying capacity means the amount of birds will not exceed 500 based off resources and their environment. The population P can be modeled by the function we see here. where T is, let's highlight that because that's going to be very useful. T is the number of years since the birds were released. In other words, we can put in different values for T to figure out what the population looks like after so many years. And with that said, we have 4 questions to answer, starting with, when does the growth rate start to decrease? Well, if you remember from our graph that looks like this, that is the point right in the middle, and we call that point the point of max growth. So if we find that point, we find the specific place where the growth rate starts to decrease. So how do we use it? There it is. You have A, B, and C, and there is A, B, and C. So you're just really picking those values out of your function. Okay? I'll give you a moment to look that over, checking, okay, A is next to E, 4.55. B, remember, is friends with dishonest H. It's a sneaky guy as well because the original function, as you see here, has minus, so it's the opposite. So if you see negative 0.5, B is actually positive 0.5. And then we have C, that's just the numerator over 2. From here, a little calculator work will give you the point of max growth and your answer to part A. B, what is the initial population? That means how many birds were in this forest preserve the moment they put them in. How much time has passed? Okay. How much time? Well, it's the exact moment they were released. So no time has passed. So we're going to set years to 0, and we're going to substitute 0 into the function they gave us. Remember, this equals 0, and e to the 0 is 1 because anything to the power of 0 is 1. So ultimately, you're going to get 500 over 5.55. If you divide that out, you'll find there were 90 birds in the very beginning. C, what's the max population? Well, that's the same as the carrying capacity, which is always equal to C, which is always our numerator. So what value is up there? 500. Done. And finally, D. What's the population of the birds after 2 years? Well, didn't we say earlier the beauty of T is that you can plug in any amount of time and find out the population? That's exactly what we're going to do. Plug in 2 for T. Notice this time the numerator will not be 0, so you're going to need to raise e to a power. The calculator is your friend at this point. Just be careful. When you plug this in on your calculator, if it's a handheld, you want to make sure to put parentheses around the entire denominator, or you'll get the wrong answer. I always recommend using the Desmos scientific calculator because it's going to look exactly like this. If you did it right, you can visually check that. So after 2 years, the population is 187. So is this forest preserve a good place for the birds to live? Possibly, because they're growing, right? We had 90 in the beginning. After 2 years, there's 187. Seems like they're doing well. And our last question, number 12. What's the domain and range of this function? There it is. We have several things going on. There's athletic A, dishonest H, and elevator V. Back again. So you can think about this. You can write it out however you want, or you can graph it to visually see it. Personally, I would choose to graph it. Okay? You can use the Desmos graphing tool, or you can graph it based off what you've learned in this class. But that's really the hard part because after that, You're just listing domain and range based off what you see. The furthest left x value is -3. And keep in mind, this is a radical function, so this point is included. We're not dealing with vertical asymptotes when we're looking at this problem. So that point is included. That's the furthest left it will go, but it will go right forever. And the range, what's the lowest point? I see -1. And how high up will that line go? Once again, forever in the positive direction. We've done it. We've gotten to the end of our practice test. Don't forget to finish taking your notes, study, and turn it in.